In this section, we will be looking at finding volumes using cross sections. So we're going to be working with three-dimensional figures in this section. And the first way that we're going to find volumes is by taking a typical cross section of the three-dimensional object. So for this type of problem, the solid has to be a uniform sort of shape throughout. If you look at this picture here, it does change in terms of the size, but the proportions are the same. They're similar figures throughout. They are just dilated as you move from the center, which is the smallest, to the ends at A and B, which are the biggest. So this method only works if we have cross sections that are the same shape throughout. They just get dilated, bigger or smaller versions of the same shape. So there are a few different ways we can look at it. We can go that way. We can have a base, and then we can have the height coming off of the coordinate plane. These solids can really be sort of any orientation that we want. And again, this just shows the same image as the first slide, and it's got a second slice there, which is x sub k and x sub k minus 1. Those are both the same relative shape, slightly different sizes, so they're going to have slightly different areas. What we're going to do is we're going to take up a bunch of these little slices, and we're going to add them all up, and that will become volume. It's just like taking the Riemann sums to get the integral. And that's why it's in this chapter, is because we're going to be taking a bunch of small pieces, accumulating them, and getting a larger value. So we're going from an area, taking an integral, which becomes a volume. Here's the formula for it. All we're doing is integrating an area. So the volume of a solid of integrable cross-sectional area A from x equals a to x equals b is just the integral of the area. So the integral from a to b of capital A area of x dx. So all we're doing is taking the integral of an area. The most important thing that we are going to be doing in this is figuring out the formula for the area. If you don't know the formula for the area, you're not going to be able to integrate something. You can't integrate a constant. That is not what we want to do. We don't want to take the area of one cross section and try to integrate that. That's not going to give us a solid that has different dilated portions throughout. It's going to give us like a cube or a cylinder, something that has a constant width, constant radius. And that's not necessarily what the images, what the solids they're going to give us will look like. So we have to have something that is a variable in the area so it can change throughout the solid as we move along it. So there's the same picture for a third time. We're going to skip over that. So what we want to do is we want to sketch the solid in a typical cross section. You don't necessarily need to do that. If you can understand what's going on without a picture, great. But if the picture is helpful, always draw a picture. The most important part again is finding the area formula A. Then we want to find the limits of integration. Those are going to be off the axis that you're integrating. So the formula that they gave us here, we're integrating area variable x, so that is from x equals a to x equals b. We want to get those limits of integration from the axes. And then we are going to actually do the integrating with the fundamental theorem. What they meant to write there when they said fundamental theorem is calculator. So we're going to use the calculator to find all of these integrals. First example here is a pyramid. Now we've hopefully done these volumes in geometry. So the first thing we're going to do is calculate the volume of this pyramid with geometry. So the volume formula for a pyramid is 1/3 big base times the height. So 1/3 base area times height. And for this specific pyramid here, the base is a square, so that's going to be side squared. So 1/3 sides of the base squared times the height. Okay, so the base has sides that are 3. So put that in there, so 3 squared. We still have this 1/3 out front. And then the height of this, it's kind of weird to see with the perspective they've drawn here, but the end of this rectangle ends at 3. Or sorry, this square here ends at 3 on the base. So the height of this pyramid is 3. So when we do all that math together, we should end up with 9, a volume of 9. So we just have a frame of reference. When we come through with the calculus, we should get an answer of 9. We can verify that with geometry, as we've done for some areas in previous chapters. Now what we need to do is we need to come up with the area of a typical cross section. So they have that red square there to show us what a typical cross section is. The cross section of this is the same as the shape of the base. Sometimes for more standard geometric figures like this, they'll not give us additional information. We have to figure out, oh, hey, that's a square-based pyramid. Okay, the cross section is going to be a square. Oh, that's a cone. Well, the cross section is going to be circles. Easy things like that, they might not come out and tell you. For the problems that we're going to see down here a little bit, they will tell you what shape they want you to use. Either way, you need to know that area formula for whatever shape that they're asking about. So the area of a square is sides squared. We're not going to use the s variable here. We're going to use the variable that they've given us, which is x. So the area of this typical cross section, this square cross section, will be x squared. That's what we're going to integrate. We're going to integrate the typical cross section, x squared dx, and then we're going to take our limits from the x-axis. So the x-axis, they start us here at 0, so that's our lower limit, and we end here at 3, so that's our upper limit. Could you do this integral by hand? Absolutely. Should you be able to? Yeah, undoubtedly. Are we going to? No. We're going to use a calculator here and let it do the work. Very quickly, we're going to run into integrals that we can't do by hand, so it's a better idea just to get going on the calculator now. And we see when we take that integral from 0 to 3 of x squared, we get 9, which is exactly what we got with geometry. So this is verified. It works. It gives us the same thing we found in geometry. The volume of this pyramid is 9. So this is not the primary use of this. We know how to calculate areas like a pyramid or a sphere or a cylinder, cone, whatever. We know how to do that with geometry. So we want to get into some more complicated shapes that we wouldn't have a geometric formula to get the entire volume of. And that's what we're looking at here. So this is a solid made with the base that has the area, the base here, from the x-axis up to this curve y equals 2 sine x. Probably not a great idea to draw in red, one that's already in red. So we'll draw in green. So this is the function 2 sine x. The cross sections are going to be perpendicular to the x-axis. They'll always tell you what axis they're perpendicular to, that way you know which way they're running. Perpendicular to the x-axis, they are semicircles whose diameter runs from the x-axis to that curve that they just mentioned, 2 sine x. Okay, so what we want to do here, back to the steps, is we have a picture. Okay, that was step 1. Step 2 is figure out the area formula for a typical cross section. So they said each cross section is a semicircle. So you always want to find that statement in the problem. Each cross section is a whatever shape they have. So a semicircle. So we need to have the area formula for a semicircle. So the area formula for a circle is pi r squared. So this will be pi r squared over 2. Okay. So we now need to do a little bit of intermediate work before we can start integrating that. The information they gave us doesn't mention radius in the problem at all. What they mention is the diameter. So the diameter runs from the x-axis to the curve. So the diameter is going to be, and this is what will happen anytime that they're giving you two equations like this in the coordinate plane, to find the side length between them, or the diameter, or whatever the measurement, the name for it is, you're going to take the functions and subtract them. So our top function here is 2 sine x, and the bottom function is the x-axis, or y equals 0. So we don't really need to write that, it's trivial. So the diameter of these semicircles, which is what they said, runs from the x-axis to the curve, has a length of 2 sine x. So the radius for that would be half of 2 sine x, so just 1 sine x. All right, now we have all the pieces we need, those two pieces, to set up the integral. So if you want to take a shot at that, go ahead, pause the video, and try to set it up. So our integral here is pi over 2. Those are constants, so I'm just going to write them right there. Radius squared, we said radius was sine x dx. And then the limits of integration, we're going to take from the x-axis, so from 0 to pi. Again, we're going to take our limits of integration from the axis that our variable is written in. So our variable here is x. We're going to take our limits from the x-axis. All right, so once we have that all set up, that is the hard part. Now we are to the calculator. We just got to hit the right buttons in the right order, and we should be good to go. Not the prettiest way to write that, but there we have it. Pi squared over 4. And again, we could probably do this one by hand. We would have to do a u substitution, but we could get through it. It's actually, no, it's probably a harder problem since there's no cosine anywhere. Use the calculator. Don't spend any time trying to do these by hand. Just go ahead straight to the calculator and calculate the volume. All right, so the next part that they give us, which was a big deal, it's Cavalier's principle, but it makes a lot of sense once you look at it. Basically, these two shapes, this curved sort of looking macaroni noodle here and the straight cylinder, have the same volume. And the principle, basically, the easiest way to think about it is if you take a stack of quarters. It's got a definite volume. It's x number of quarters times the height. It's definite volume. If you take that stack of quarters and you just push at different points on that stack of quarters so they're no longer in a perfect column, you haven't changed the volume. You haven't taken anything away from that stack of quarters, but you have changed the way it looks. It's going to look more like this squiggly noodle here than this straight column. And that has the same volume because you've not taken anything away. So quarters are thick. If we take increasingly thin slices, we would get to that same principle of stacking a bunch of slices to get a volume. And as long as those slices are the same, corresponding from the curved noodle to the straight noodle throughout, then they're going to have the same volume. So we don't really do anything with that. It's just sort of a principle they give us, and it's related to this volume from a typical cross section. And they even talk about stack of coins. So one more example we're going to do over here with these cross sections. We've got all of these printouts here. We'll do this one right here. So it says let f of x equal 5 minus x. So that is this top f function here, the blue. And g is 2 sine pi x over 6, which is this red curve here. R is the region enclosed by the graphs and the y-axis. So they've got everything shaded in for us. So they've taken half of the picture and drawn it for us. We need to draw the other part. So region R is the base of a solid. So that means our solid is going to be coming out of that region. It's kind of hard to draw 3D on a 2D screen, but hopefully you get the idea there. So for each x value, the cross-section of the solid taken perpendicular, so here's what we want. Cross-section, perpendicular, they tell us the axis, and then is a rectangle. So they have to give us those pieces of information. Cross-section is a rectangle, perpendicular to the x-axis. Okay. Which means if it's a rectangle perpendicular to the x-axis, it's like what I just drew, but not as terrible, something like that. So the height, that's the same as the base R, and it's coming down, and it's very hard to draw that in perspective, and then there we go. So it's a rectangle coming out of the screen. Okay, so the one last piece of information they give us is the height is 2x. So what we want to do is, again, write the area formula for the rectangle. We know that formula is base times height. They have given us the height, it's 2x. So we already know height is 2x. So what we need to find is the length that's in the base. And the way we do that is the same way that I just showed in the previous example. to get the length from f to g, we're going to take the difference of those two functions. So the function f is 5 minus x, so we'll start with 5 minus x, and the function g is 2 sine pi x over 6. So 2 sine of pi x over 6. Okay. So we have the base and the height. This whole mess is what we're going to integrate. Again, not something we want to try to do by hand. That's why we're using the calculator. This would be a very challenging integral to try to do by hand. The last piece we need are the limits of integration. So we're going to look on the x-axis. So this starts at 0 on the x-axis and it goes to 3 on the x-axis. So those are our limits of integration from x equals 0 to x equals 3. Since we are integrating with respect to x, we get our limits from the x-axis. So if you want to take a moment, pause the video, set this integral up, see if you can get it. Maybe you can go ahead and get a calculated value. Do that at this time. Okay, so the first thing to set up on the integral here, again, are the limits. So it's from 0 on the x to 3 on the x. Those are the x values. We have the area formula, which is base times height. So the base, again, was all of this. So 5 minus x times, 5 minus x minus. I wrote that wrong. Hopefully that didn't mess anybody up. 5 minus x minus 2 sine pi x over 6. So that's the base. Close, close, close. There we go. Times the height, which is 2x. So it's a lot going on there. Again, not a nice integral to have to do by hand, but we're not doing it by hand. We're going to use the calculator. So we go from 0 to 3 of, now we're going to have to do triple parenthesis here, and to double parenthesis. 5 minus x, close that one, minus, open another one, 2 sine, there's our third parenthesis, of pi x over 6, and then close, 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 times 2x, close that, dx. All right, let's see what it gives us. All right, there we go. That is a lovely mess. And again, that's not something we want to calculate by hand. We could probably simplify that. Let's see. Be like 27 minus 144 over pi squared. I would definitely take it as the calculator displayed it there. Unsimplified is totally fine with me. We have pi minus 16 all over pi squared. Okay, so there we go. And that is the sort of gist of it here. The setups do get a little bit more challenging when there are different shapes. Squares are the easiest shape to set up because it's just whatever the base is and you square that. Semicircles are then the easiest. You take the base length and divide it by 2, that's your radius. When we get to triangles, triangles are the most challenging. So equilateral triangles and hypotenuse triangles, those are much more challenging to do, and you have to use the 30, 60, 90 relationships and the 45, 45, 90 relationships to try to calculate those side lengths. So those might be a little bit out of the wheelhouse to start, but those are also in there. These 3 examples here, these are really good examples. You start with a circle. So the first thing you'd have to do for those is rearrange that circle equation to be the square root of like 16 minus x squared, the positive and negative square root. So you'd have 2 functions really there to work with. And then the cross sections, again, are kind of the same there. Hypotenuse of a isosceles right, semicircle in the plane, and then equilateral triangle. So if you want to get any of that information from those, pause the video on those places. But that wraps it up for this section.